So we're going to start with a sample diploma question, so make sure you try these on your own before doing them with me. Two identical conducting spheres are fastened to electrically insulated stands. The charge on one sphere is greater than the charge on the other. So we are trying to figure out the magnitudes of the forces if we drew a free body diagram. So you have to remember that with Coulomb's law, Fe equals K Q1 Q2 all over R squared, right? It doesn't matter who Q1 is, who Q2 is. They're going to exert an equal and opposite force on each other. So D is the correct answer. Two identically charged objects are placed near point P. Which of the following draws the force? Cool, so they're the same charge, right? So if I were to draw this, let me draw this one first. So this is positive, this is positive, this is positive, everything's positive. So this first charge here, this is 1, this is 2. This would be, oops. Sorry, I accidentally ended my show there. Let me try this again. There we go. So this is force of 1, right? And you have to remember that Fe equals Kq, Q1, Q2, all over R squared. So nothing's changing between the two of these, right? If we look at these ones and then we look at these ones, Q, they're all the same. The only thing that changes is the distance, right? This has a distance of Q2, 2Q, so this is double the distance. This is half the distance. So if we half our distance, right, that gets squared. We do nothing on top. 1 squared is 1. 2 squared is 4. 4. We're going to have 4 times the force. So this one should be, force 2 should be 4 times bigger, and that's what we're looking for, right? So C gives us a better answer than A, because this looks like double the size. This is 4 times the size, so C is the better answer. Okay, Coulomb's torsion balance experiment. They want to know the angle of the twist in the fiber measures. So the twist in the fiber measures force, and it's directly proportional to, so it's directly proportional to the charges. It's inversely squared proportional to the radius. So the product of the charge on each sphere, yeah. And this one here, match the numbers, the direction, and the force with the largest magnitude, okay? So we have our force of gravity down. We have our force of tension that way. And then we have our Fe over here. So if we add those tip to tail, well, that gives us the first two, right? So force of gravity is down, so that's 6. Force electric is that way, so that's 4. And then if we draw these tip to tail, right? So we have Ft, Fg, and Fe, right? That makes a right angle triangle. Our Ft is our hypotenuse side, and your hypotenuse side has to be your longest side, which means that no matter how we set this up, our force of tension is going to be the strongest. So today we're going to talk about electrical fields. Anyone know what movie this is? It's Field of Dreams, but we're talking about electrical field of dreams. So curriculum, define vector fields, compare forces and fields, explain quantitatively electric fields in terms of intensity, direction, relative source of the field, and the effect of electric charge, plot field lines induced by discrete point charges, combinations of discrete point charges, and charge parallel plates. Okay, we'll go through all this, nothing to point out there. Force. Push or pull, nice and easy. We can figure this out, right? You push, you pull on something, that is a force. A field is a little bit differently. So what I use for field is I use an analogy. So here we have some oiled up buff dudes. And these oiled up buff dudes create an oiled up buff dude field. So if you like these oiled up buff dudes, so if you think, I would like to touch their bodies a little bit, I would like to rub some oil on them, what you're going to feel is you're going to feel a force from those oiled up buff dudes, right? So this is you like them. There exists these oiled up buff dude field, which is just a 3D area of space. That's our field that we're going through. And if I go through it and I like the oiled up buff dudes, then I'm going to experience a force from those oiled up buff dudes, right? But if I'm the wrong test object, if I don't like those oiled up buff dudes, they do nothing for me, this field still exists, even though I don't like them, I travel through it and I experience no force, right? So what you need is you need a source. So these guys are my source. They create the field, and then you need a test object. Sometimes your test object experiences a force, sometimes it doesn't. That's my analogy. So fields are a 3D space around an object that can influence that object. And I should say a 3D area around a source. I like that better. That can influence a test object. It can, right? So the effect produces a force. So if you are the right test object in that field, then you experience a force. So there's different types of fields. There's scalar fields like temperature and sound, and they only have a magnitude, just like all scalar things. But we don't deal with these. We deal with vector fields, right? Which means that along with the magnitude, you need a direction. So gravitational, electric, and magnetic fields, they need a direction with their answer. So what causes a gravitational field? So what's my source, right? A gravitational field, the source is a mass. Anything with mass creates a gravitational field. And yeah, like planets, us, anything like that. So we have Earth here, let's say, and this is the surface of Earth. So this is when we are 6.37 times 10 to the 6 meters away from the center of Earth. And what we experience is we experience a gravitational field of 9.81 meters per second squared, or newtons per kilogram. And what direction? Well, that's towards the center of the Earth, right? We experience this gravitational field. Okay, so this is how we calculate a gravitational field. G, gravitational constant. Little g is gravitational field, and m is mass, and r is our distance from the center of the mass. Right? We can draw these field lines in right here. So these field lines show the direction and they show the magnitude. The way they show the magnitude is with the density of the lines. So as we go further away, you can see they get less spaced together. When we're closer, they're more spaced together. So the density of the lines represents the magnitude, how strong the field is. Calculate the gravitational field on a 10 10 kilogram object on Earth's surface. Well, this is easy. We can use G equals gm divided by r squared. So 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared is our gravitational constant. And this mass here, well, do we want this 10 kilogram object in there, or do we want the Earth, right? And it's important to know that when you're calculating this mass, you want to use our source. And our source of the field is the Earth, so we have to as our mass, and this r is the distance from 0.81 meters per second squared. So whenever we're on the surface of the Earth, we are average 6.37 times 10 to the 6 meters away. We experience that as our gravitational field. So electric field is basically the same idea. So what causes an electric field? Well, think about what would give something an electric field. Well, we need a charge, right? So we can have a positive or a negative charge, right? So a charge is our source of our electric field. The tricky part is if we have a positive charge, is it towards the charge? Is it away the charge, right? Because we have two different types of charge. So what if this is positive? What if this is negative? How are we going to figure this out? The formula is basically the same, right? E equals kq over r squared. So switch g with k, m with q, all over r squared. Same idea, right? Instead of newtons meters per kilogram squared, it's newtons meters per kilogram squared. That's nice and easy. But how do we determine the direction? What does the electric field look like? Well, to find the direction of an electric field, you just have to ask yourself, what would Pedro do? So who is Pedro? Well, Pedro is, I have a real thing in real life. This is Pedro, and he is so happy, right? He's, hi guys, I'm Pedro, and I will help you find the direction of an electric field. So Pedro is an awesome guy. Pedro is always so positive. So to find the direction of the electric field is the direction a small positive test charge would move when placed in that field, right? So a test charge is just an imaginary positive charge placed in that field. So if we put Pedro, hi, I'm here. Yes, this is me, Pedro. Hi. So if we put Pedro there and Pedro's positive, Pedro would be repelled, right? So Pedro would go away, Pedro would go away, Pedro would go away. No matter what direction, no matter where you put Pedro, he would go away, right? And then if you put Pedro here, he'd be attracted to it, and no matter where you put Pedro, he'd be attracted to it, right? So you can see the electric field around here. So the electric field looks a little bit different if you have a couple different charges. There we go. So let's put on this grid. So if we have a positive and a negative charge, let's get rid of that electric field. And let's put in our sensor here, right? So if we had a positive and a negative, it would always sort of go towards that negative. So this is Pedro. This shows what direction Pedro would go, right? And if we were close to the positive, it'd be repelled until we got about here, and then it would start to get attracted to this one. So this would be our field lines around it, right? Same thing. This would show our field lines around it, like that. Right? And if I was on this side, I would just be repelled. If I was this side, I'd just be attracted no matter where I went. So we can draw that in, right? Pedro would be away from the positive towards the negative. It would look like that. And then over on this side, it would be away. This side, it would be towards. So that's what it would look like. So if we had two positives, it would look a little bit different. So if I replace this negative with a positive, right, you can see that Pedro's repelled on this side. Pedro's repelled on this side, right? This one's closer, so he's more repelled from this one, and then we start to get closer and closer to the middle, and then right when we get in the middle, you see that there's no electric field. But then we start getting closer to this one, and it repels more that way. If we go up here, it's repelled by this one, and then as it goes to the middle, it's repelled equally by both, so it would end up going up, right? Same thing down here. So we can draw that on here. It's repelled until the middle, repelled into the middle. gets repelled like this, repelled like this, repelled like this, and then just normal repelled this way. So if we had two negatives, it would look pretty similar to two positives, only our direction would change. So let's switch out our negative, our positive with a negative, right? I'd have no field right in the middle, but here I'd be attracted, here I'd be attracted, right? I'd be attracted, attracted, and then I'd sort of go straight up. Same here, I'd go straight down because both of the x's are canceled out and you just have y's. I'd be totally attracted to this one, totally attracted to this one on this side. So we can draw that on, right? So in the middle, we'll just switch the direction of the arrow. I'd be attracted like this, attracted like this. And then on this side, just be attracted to it. So you need to know what these look like around discrete charges like this. Yeah, that's pretty much it. So there's a couple different types of questions we can have. Determine the electric field 90 centimeters north of a negative 9.5. The negative didn't make it way down here. A negative 9.5 microcoulomb charge. Okay, so we have our negative 9.5 microcoulombs charge. And here we are 90 centimeters north of it. Yeah, so the magnitude is easy. We can use our electric field equals KQ divided by R squared, where K is 8.99 times 10 to the 9 newtons meters squared per coulomb squared. That's a 9. That's a 10. There we go. So our charge is 9.5 micro, so times 10 to the negative 6 coulombs. And then our distance is 90 centimeters, or 0.90 meters. Can't forget to square that. So if we plug that into our calculator, just wait for it to open up. Almost ready. How's your day going so far? There we go. So we can just go alpha k times 9.5 times 10 to the negative 6. And then we divide it by 0.9 squared. And we end up getting that it's, what was that, 1.05. 1, 2, 3, 4, 5. 1.05 times 10 to the 5 newtons per coulomb, right? But remember that this is a vector field, so if we're above, we need to go this way, and we use north and south already, so Pedro would be attracted towards the negative, so my direction would be south. So this one here is just a 2D version of the same thing. 2-point charges are aligned as shown in the diagram. Determine the net electric field at point P. Remember that this point P here stands for Pedro, so there's Pedro there. So first thing we need to do is draw, it's not a free body diagram, but it's the same idea as a free body diagram. It's like a free body diagram of the field. So Pedro here, this is 1, this is 2. So if Pedro was sitting here, well, Pedro would be repelled by 1. So I would draw it like that. So that's my electric field from 1. Okay, and then Pedro here would be attracted to this negative. It's a little bit further away, so I'm going to make it a little bit smaller than the first one. So the electric field from 2 would look like that. Okay. It's easy enough to get magnitudes. I'm just going to plug those into my calculator to get magnitudes. So if I move it down here, can I make it any smaller? Yes, I can. So the electric field created by this when it's 6 centimeters away would just be alpha K times our charge, which is 3 microcoulombs, divided by 8 centimeters. Oops, not 8 centimeters, 6 centimeters. And then I got to square it. Right, so we're using E equals KQ, all divided by R squared. KQ divided by R squared. That's what we end up getting. Okay. I can do the same thing for the other one, but instead of being 3 microcoulombs, it's 2 microcoulombs. And instead of being 6 centimeters, or times 10 to the negative 2, it's 8. So that's my other one. Right, so those are my two magnitudes of my field now, because if I add this tip to tail, this one's longer, then I have this one, right? I don't make a right angle triangle, so I have to do an RCS chart. So that's what I'm going to do. And I'm going to do an RCS chart like this. I'm going to keep these guys handy. So with my RCS chart, so we have electric field 1, and it is the 7.49 times 10 to the 3, 4, 5, 6 newtons per coulomb, and it's straight east, so it's 0 degrees. And then the other one is 2.80 times 10 to the 3, 4, 5 newtons per coulomb. So this is my electric field 2. And then that one was going, it was like this, 42 degrees below that. So this is 360, so 360 minus 42 is going to be 318 degrees. So x is at 7.49 times 10 to the 6. Cos of 0, 2.80 times 10 to the 5. I'm going to use the full numbers. Cos of 318, 7.49 times 10 to the 6. Sine of 0, and 2.80 times 10 to the 5. Sine of 318. So that's what I'm going to plug into my calculator, but with the full numbers. That's why I didn't even round it properly. So let's do that. So I'll go this, cos of 0 plus this cos of 318. Right, so that's my total x. And then if I push center, second enter, I can switch all my coses to sines. And that's my total y. Yeah, looks good. So I can draw my final triangle. So my x is positive, so 9.58 times 10 to the 6. And then my y is negative. It is 1.88 times 10 to the 6. So this is my net electric field. So I'll have to go this squared plus this squared, square root it. So I'm going to take this squared plus this squared, but I'm going to get rid of that negative, that pesky negative. And I'm going to square root it. And then I'm going to square root it. So my net electric field is 1, 2, 3, 4, 5, 6, 9.76 right? I also need to, it's cool, I need to tan -1 opposite over adjacent, so tan -1, the 1.88 over the 9.58, and it should be some small angle, so I'll do that as well. So I'll tan -1, the 1.88, get rid of that negative, divided by the 9.58. It should be tiny. Yeah, so I get 11.1 degrees. And that's going to be south of east. Yeah, I got my answer. I'm all done. That's how I do it. So a Faraday cage is an enclosure made of conductive materials. It protects against electric fields. If you have computer equipment, it's sensitive to electric fields because electrons are trying to move down a wire, but if you have an electric field one way, it'll attract those electrons. So biggest thing that you have like a big charge suddenly somewhere would be lightning strikes. So yeah, that's what a Faraday cage would protect against is lightning strikes, and it's called shielding computer equipment is what it is. So if you have a conductive material around it and there's a charge close by, what's going to happen is, oh, that was weird. There we go. Is the electric field inside of here is going to be 0 because if you have a bunch of charge around here, Pedro would be attracted to all of them equally, so it would cancel out. So if you just have a conductive material with it, if there's electrons around it, it'll cancel out the electric field. So yeah, this is your homework. Give it a go, and that is all.